Hi, everyone. It's really nice that you guys are here. And I'm Tiancheng here from Polyhedra Network, and I'm co-founder and CTO. And today, I'm going to present the proving full node of Ethereum in the general proofs. And we are going to present more stuff here. So bridges is our main product. And it's a very risky one, because as we have witnessed a lot of bridge accidents. Over 1.5 million assets has been lost in last several years. And to mitigate these vulnerabilities, we have proposed a ZK bridge. It's based on a zero-knowledge proof. And using zero-knowledge proof, we can minimize the trust, and we can much simplify the smart contract development on-chain. And more exciting thing is that we have delivered more than millions of messages since we launched. So the core mechanism of the ZK bridge is we use zero-knowledge proof to prove the consensus. And we have integrated a lot of different chains, layer 1 and layer 2. And in this diagram, it's a framework of ZK bridge. And as you can see here, we have two blockchains. On the purple side is sender, on the blue side is a receiver. And our proof network will monitor the sender chain status, and it will prove the consensus of the sender chain using zero-knowledge proofs. To be more specific, let's say sender chain is Ethereum. Then the proving task will be you prove thousands of signatures from validators that has signed this block, and supermajority of the validator has agreed on this block. After the block is proved, it will be sent to the receiver side for verification. And if a receiver is convinced that the block is actually correct, it will store it. And the user can retrieve their transaction from this block and do more operations on the receiver chain. So to enable this proof of consensus, we need to innovate on the proof system. So today, I'm going to present a next generation of zero-knowledge proof. It is actually the fastest zero-knowledge proof system. And here is the structure of the proof system. So we use a basic component algorithm. It's called Virgo. And it's based on the GKR protocol. It is extremely fast that can process millions of constraints on a single CPU core. And in dVirgo, we combine all of this processing power in one proof system. And we can prove very gigantic circuit in this proof system. And furthermore, we will use recursive proof to compress the proof size so that the proof can be efficiently verified on-chain. And this proof system is the world's most advanced proof system. In a single CPU core, it can process like 3 million of constraints per bit per second. And it requires extremely low memory. And if you combine all of these CPU cores together, you can prove billions of circuits, billions of size in terms of circuits. So let's look at Ethereum specifically. To prove a full node consensus, we need to verify like at least 20,000 validator signatures. And these validators will rotate frequently. And the time limit is actually 12 seconds, because Ethereum will generate blocks every 12 seconds. If you compare it to a growth system needs more than half an hour to generate such proofs. And our proof system is much, much faster than gross system. This is our proof system. Both of the line are our proof system. The blue one is we run our system on a giant server, which has 2 AMD most advanced CPU installed. And the purple one is we run our proof system on 64 smaller devices. And this is much faster because we have a lot more CPU cores. And to give you some idea, the proof generation time will be like 5 to 6 seconds on our smaller device. And the energy consumption is kind of negligible per proof. So people may talk about decentralization of proofs. Decentralization of proof is extremely important because we want to encourage everyone to generate zero-knowledge proofs. The major roadblock of generating zero-knowledge proofs is that usually zero-knowledge proof requires a huge machine that costs more than $10,000 US. This is a huge upfront cost for average miner or validator. So in our proof system, we reduce it to a very low spec machine. And I will present it in our deck here. Here is our machine. This is a gaming console developed by the Valve Corporation. And some of you may know that they have a great gaming platform. It's called Steam. And this is a Steam Deck. This machine costs about $400. And you can purchase a lot of them from the Steam Deck, from Steam. Yeah, and for validator to become a ZKP prover, you only need one of this machine. And to finish our Ethereum zero-knowledge proof, we need 64 of them. But it's okay that they can be globally distributed. The communication cost is actually low. So this is kind of a pool of zero-knowledge proof machines. In summary, we have very low hardware requirement. The only thing we require is you have a stable internet connection. We don't want you to drop off during the proof generation. And the CPU and the RAM spec requirement is super low. So next, I'm going to do a demo. And yeah, please switch to my deck. Here's my Steam Deck, and I bring one here. Of course, I cannot bring 64 of them, so this will be a one-machine demo. And first, let me show you the Steam spec. So we are running the prover on Steam OS, and the hardware is we have 8-core AMD APU. This is very cheap APU, by the way. And the RAM consumption is lower than 16 gigabytes of RAM. And to prove that I'm not using a video, I'm going to go to Etherscan, refresh it. And I'm going to pick the latest block. The latest block hash will be here. Let me find it. It's really hard to navigate using Steam Deck. Yeah, here's the latest block hash. You guys can check. I'm not recording a video, and I'm not playing a video here. You can check this like 10 seconds ago. OK. Now I'm going to go back to the console here. So I'm going to run a signature verification algorithm, proof generation algorithm on 256 signatures. And the 8 is actually 8 CPU cores. This machine has 8 CPU cores, so I write 8 here. OK, it's proving it layer by layer. So it's a GKR algorithm. And as you can see, we proved in 3 seconds. And if you're going to look at more larger circuit, for example, here is a circuit of size 1024. Let me show you here. Here's a proof circuit of size 1024, and the time will scale linearly. It should be like around 10 seconds. OK, like 12 seconds. Yeah. So if you are targeting like Ethereum blockchain, you could use this 124 configuration, and you will need like 32 Steam decks to finish the proof. Yes, finish the demo. Yeah. Thank you so much. So with this proving power, we can actually do a lot more. And we are trying to propose that we are trying to propose to Ethereum that we can actually put all validators into one slot. And this will achieve very fast finality and improve scalability. Let me show you why. So in current Ethereum solution, we have around 1 million validators. And here is a smaller scale the illustration. Assuming that this is 1 million validators. And in current Ethereum solution, they will divide this 1 million validators into 32 groups. And here we are divided into 4 groups for demonstration. And each group is named a slot. So they will have like 32 slots for epoch. And if you want to, a slot is a block, actually. So slot is equal to a block. If you want to achieve like confirmation, you will need supermajority of validators sign your transaction, which means that in this diagram, you need 3 blocks to approve your transaction. So you need to wait for 3 blocks. And if you are in real Ethereum, you need like 20 blocks to confirm your transaction. So the confirmation time is actually several minutes. And why does they do this design? Because their P2P network has overloaded. So here is an example of P2P network. If you have a very small slot, then your P2P may be OK. The load of this P2P network may be OK. But if you extend it to the whole validator set with 1 million validators, your P2P network will be super messy, and they cannot handle it. So with a zero-knowledge proof, we can do the following. Instead of sending signatures or gossiping signatures in the network, we prove the signature are correct. So actually, the validators only want to know that their neighbors, whether their neighbors are honestly signed it or not. So we don't directly provide signatures in a P2P network. Instead, the validators generate zero-knowledge proofs. And proofs is extremely short, so they can communicate more efficient. And this P2P network will not overload. So we can put every validator in a single slot. And with this, we can scale. We can basically confirm every transaction in one slot. So you only need to wait like 12 seconds to confirm your transaction. And for timeline, we are doing our CPU implementation of our prover, and the efficient distributed GKR has been implemented as a demo here. And next several months, we are going to do a mid and large scale testing. And for next step, we are going to schedule a GPU implementation, of course, and compiler implementation for our circuit. And currently, we are using GNARC, which is a great compiler. And this compiler is super stable and super efficient. Their front-end language is super easy to use. So we recommend you guys, if you are interested in developing ZK circuit, you can try GNARC. And we will also build our compiler upon their front end. And we are open to discuss on ideas on optimizations. I think this concludes my talk. Thank you so much. And yeah.